Hello, this is the Harp Report, and today I'm going to show you two of these Hawaiian hurricanes that approached the islands. It looked like they were aimed to hit the islands in early September 2018. The first one is Norman, and as it was back far away, the eye was very fragmented. It kept breaking up and reforming along the straight line track, and I believe it was being aimed at that time. Let me show you. So you can see it. It's doesn't have much of an eye. It keeps breaking apart, reforming right there, and it looked like it was really to fine-tune the aim. You know, just a few days later, a couple days later, Hurricane Olivia came through there, and it was a solid round eye the whole way. So this Hurricane Norman, the first one, appears to be something strange going on with it. So let's not forget Hurricane Lane, which was just a week or so ahead of Hurricane Norman. It came up in sort of a curve like this, and then it was completely destroyed right in this area. So that's 3 direct hits on Hawaii in about a 2-week period. So how unusual is that? Well, it's extremely unusual. Here's 66 years of hurricane tracks and tropical storm tracks, and only one major hurricane hit the Hawaiian Islands, and that was Hurricane Iniki. The only other hit was a tropical storm, and it looks like it was called Ezel, orange color tropical storm. So only 2 hits on the islands in 66 years. And suddenly we have 3 in about a 2-week period. So I believe that we may be seeing basically a low-level international conflict using this weather control hardware. And I would say that if it's the Chinese or the Russians, who knows, could be really several countries aiming these hurricanes at a U.S. Navy base. They're not doing it to be aggressive. They are doing it to force the U.S. Navy to show its hand and then reveal this technology to the world through little guys like you and me, through our efforts. And at that point, then you can have like a JFK 1962 test ban treaty. Because the last thing in the world we want is a ton of these microwave ships floating around, each zapping the ionosphere, because each time they do that, they blow some of the atmosphere out to space, and it's lost. And underneath that hot ball of plasma, rapidly expanding gas, it punches a hole in the ozone layer. So the last thing this planet needs is multinational fleets of these ionospheric heaters playing tit for tat with these hurricanes and storms. So I think I see this in the international context as being a very positive thing, that is going to force the U.S. Navy to say, yeah, we do have this technology. And let me show you what happened. Well, first let me just summarize Hurricane Norman. There is a strong area of shear here, and it was always predicted to come up into this area of shear and then just blow away, which it did. But there was some anomalous behavior. Incidentally, this low pressure remnant from this thing did blow up far north of Hawaii, where the jet stream held it in a pocket. It could have blown into California and brought rain, but instead it was held in a little pocket until it dissipated and fell apart. Let's look at Olivia now. So you can see there's right here's the remnant of Norman, and easily this could have been swept into California. Instead, they held it in this pocket until it fell apart. So California drought, this is the cause right here. This is the cause, and Oahu's playing a big part in this. So down here is Olivia approaching, and they took this very seriously. It was forecasted to be a major event. And again, some signs that Olivia may be getting steered as it goes. But even a week out, they were predicting a straight line hitting the Hawaiian Islands. So in visible light mode on September 11th, it's still hanging together, Olivia, moving towards the islands. And the key here is that it's now got clear line of sight and it's within 450 miles. It's right on the cusp of the range. And the reason the ionospheric heater has a range of 450 miles is due to the curvature of the Earth. So here's a transmitter that has a straight beam, and it is going to heat the ionosphere up here about 50 miles high. So if you do the trigonometry on that, the longest distance that it can go shooting right at the horizon, it's a tangent to a circle, is 450 miles. So as it enters the range, the effective range, it gets blown apart. The top is blown apart, blown away. The upper low pressure disappears, but the bottom, the lower level low pressure continues towards the island, and that's what caused some of the tropical storm effects. So here you see the top getting blown away, and we see the swirls at the bottom there. Nighttime. Okay, so we can actually look, well, before I do that, here's water vapor mode. You can see it gets within range, and not only is it blown apart, it turns clockwise. And I can't enlarge this. You can see it right there, turning clockwise. How the heck does that happen? That was a very powerful hurricane. It's because the upper winds, the upper atmosphere is getting warm air. The ionospheric heater is pressing down on top of the jet stream right there. I firmly believe this. I mean, a little bit of wind shear is not going to cause it to turn clockwise. Here's a better view. So this operation actually separated the storm out into a low level low pressure, and the upper low pressure was destroyed and actually blown away, and actually made to turn clockwise right here. I mean, it's a stunning amount of energy, and we have confirmation on this on the weather maps. Let me show you some detail now. So if we look at the geopotential height as Olivia approached Hawaii, there's a pretty remarkable thing that happens. When it's out in the open ocean, it has these pretty dense rings. Geopotential height is just a way to express the vertical motion in the atmosphere. So here's Olivia, and it has several rings and a little bit of blue there. And we step through 6 hours. It's diminishing. Once it gets into the HARP attack range, which occurs right about here, look what happens to the geopotential height. It pretty much falls. Okay, now that I got to show again. So we'll just and then once it passes the island, it's gone. So we'll start that over again. So geopotential height is a measure of vertical movement in the atmosphere. It's actually the altitude at which a certain pressure occurs. So if the atmosphere is moving up and down, then that height changes because there's a distortion in the pressure. Anyway, I'm going to do a tutorial on the HARP and the basics, and once people see that, they're going to say, oh my gosh, this is so simple. How could the military not build it? It's so powerful and so simple. So you have to wait a bit for that video. But here we're looking at geopotential height, and we want to look at the time. 12 Zulu. That means it is, well, it's just before daybreak. Okay, sunrise occurs at 1600. Sunset occurs at 400 in Hawaii. So 1200 is late night, sort of, I don't know, 4 in the morning or something. It's strengthened. So let's step ahead. So here's 18 Zulu. This is 2 hours after daybreak. Weakens. Here's 0 Zulu, mid-afternoon. Weakens. Now here's 06 Zulu. This is 2 hours after sunset. It's strengthened. So I know this is outside the HARP range, but it's still significant. Well, here it's strengthened at 12 Zulu. That is 4 in the morning. 18 Zulu. This is mid-afternoon. It weakened. Now, a hurricane, tropical storm, should strengthen in the daytime and weaken at night because it's feeding off of the heat. Warm, humid air at the surface is very buoyant and tries to rise, and that's where the energy comes from. So this is acting backwards. Once it gets inside the HARP range, it acts backwards from my understanding of a tropical storm. So again, Zulu 0 is that is mid-afternoon. 06 is 2 hours after sunset, strengthens. Now this is the important one here. What I said about the HARP shadow. Here's Oahu. Sorry it's so small. And they need to shoot this beam right at the big island. I don't think they want to fry everybody and then everybody be they'd wake up, you know, hey, my wristwatch burned up, my computer burned up, my phone burned up. I had a ringing, you know, your ears will ring, your corneas will turn white when the proteins congeal. In the old days, the guys that worked on the radars actually had a little fluorescent tube under the bill of their baseball cap. If it ever lit up, you knew the radar was on and you're being cooked. So in other words, the geopotential height increased right here because it's in the shadow of the big island. And 18 Zulu is 2 hours after sunset. Thing's gone. It's all over. So now, if my theory is correct, that they can only project high pressure down or descending air down from the D layer of the ionosphere in the daytime, we should be able to look at these high altitude streamlines or wind direction maps, and this is 200 millibars, which I think is about 45,000 feet, so it's way up there, and then we can compare the movement around this low pressure. Here's Olivia here, day and night, because if my hypothesis is right, we'll see clockwise flow only in the daytime as it's weakening. So we'll just step through and see this here. So again, we got to look at the 12 Zulu. That is before sunrise, and here it is. Of course, it's out of range. I think it's right at the edge, but there's no clockwise arrows here. Okay, this is 2 hours before sunrise. Let's step through. Hope this thing will play. There it goes. Now this 18 Zulu is 2 hours after sunrise, and we're seeing some change. Okay, 0-100, this is about I don't know, 2 o'clock in the afternoon, and sure enough, here is some clockwise movement. Here's some clockwise movement. We'll go ahead 6 hours. Here's 600. This is 2 hours after sunset. There is a big area of, there is a lot of clockwise movement now, a lot of clockwise. So this is high pressure at 45,000 feet. When this low pressure beneath is trying to turn counterclockwise, there's some kind of anomalous clockwise flow up here. Let's jump ahead 6 hours. 12 Zulu is now 4 hours before sunrise. And we still have some clockwise flow here. So that's That's one data point that does not confirm the hypothesis. 18 Zulu, 2 hours after sunrise. So now we should start seeing a lot of clockwise movement again, and we do. There's a lot more clockwise now than in the middle of the night. Okay, 0, this is like 3, 4, 5 in the afternoon. Ooh, big clockwise right here. There's an area of high pressure. This is actually an area of high pressure. Very high in the atmosphere, clockwise flow right here. Hope you can see this. It's pretty small. Let's jump ahead 6 hours. 06 Zulu, 2 hours after sunset. Still got lots of clockwise flow here. Lots of clockwise. Now here's a strange thing. It's clockwise on top of the low pressure and just really confused looking. 12 Zulu, this is again 4 o'clock in the morning. There is some clockwise. Yeah, okay, here, this is all clockwise. So, you know, I could go through the satellite maps and show you on the water vapor image that at nighttime it strengthens, daytime it's crushed. Every single, as it's approaching Hawaii. I don't know if we want to take the time though. Let's see. And 18 Zulu, 2 hours after sunrise. Big area. So now we're definitely within range of the HARP transmitter. And look, this area of clockwise descending air is not in the island shadow here. So jump ahead. 0. Now this is early afternoon, mid-afternoon. This area of high pressure has expanded, and the counterclockwise is almost non-existent. Now 2 hours after sunset. I'm not, well, here's a little bit of a, so after sunset that high pressure is disappearing. So this confirms the theory. 12 Zulu, this is again 4 in the morning or 5 in the morning. Here's low pressure flowing left, and that's why we saw the geopotential height actually build up right here. It's in the shadow of the big island. They can't mess with it here. But here is some right hand flow. 18 Zulu, 2 hours after sunrise. Looks like they pretty much whacked it at this point. So here, I don't know, something's happened. It's just kind of gone. Now it's actually behind the island. Well, it's like I showed earlier. The upper level low pressure was blown off. First they smashed it with high pressure. Smashing it with high pressure aloft. That's why it turns to the right. Whereas the surface low continues to the islands. But by that time, you know, it doesn't have much energy, so they did get some rain and some wind, a little bit of flooding, no damage. But the wind shear was very minor at this point. You know, the first Hurricane Norman, that was torn apart by wind shear. I agree with that. But this one, it should not have done this. It's just like Hurricane Lane. It gets within range, anomalous high pressure in the upper atmosphere, and the thing falls apart. Alrighty, so I'm going to make a video tutorial on the physics of the ionospheric heaters, and I hope people will you know, watch that, because then you're going to say, wow, this is so simple. It's so simple. And you know, I may be imagining things with all this hurricane steering and stuff, but I think what's really going on is if you could see the real image, it's so obvious. But after it's doctored by all this software at the GOES satellite processing center, that's when it becomes really ambiguous. What the heck is going on? Alrighty, thank you for watching. Hope this has not been too boring. Thanks.